All right, hi everyone. We're moving on to our next problem, which is called a harmonic oscillator, right? Described in Atkins 7E. And the first kind of question you should ask yourself is, well, what in the world is a harmonic oscillator? This is the formal definition. Harmonic oscillator is a system that experiences a restoring force which is proportional to its displacement. Not particularly helpful, maybe it is. What I would tell you instead is that a harmonic oscillator is a model system that undergoes idealized oscillatory motion. Right? And by idealized, we usually mean frictionless. It's perfect. Even that might be a little abstract. And so there's actually a lot of common examples that you studied in your physics class. Springs, right? Hooke's law. The force is proportional to the displacement. It oscillates back and forth. That's an example of a harmonic oscillator. A pendulum, right? Also a harmonic oscillator. And the reason that we're studying this in this context is that we might think about the vibrational motions of atoms as a type of harmonic oscillator. That's where we're headed. So I wanted to remind you of some properties of classical harmonic oscillators. And when you think about this, right, what you really should think about, or what you often think about, is a weight on a spring. Ink color, okay, black. So we have some weight which is attached to a spring. That weight has some mass m. The spring has associated with some spring constant k. You imagine pulling this thing down and plucking it. And what will happen is that the mass will oscillate back and forth between these two positions. So you could imagine plotting the position of your mass as a function of time, and it will undergo oscillatory motion. The specific equation which describes this is given here. These points where this thing turns around, it goes from one spot to the other, are called turning points. So I'm going to call this negative x turning point. This is x turning point. And if I have an idealized frictionless system, right, this is perfect. It will just keep bouncing back and forth, and away you go. Now, one important consequence of all of this, or one important property of all of this, is the energy of the system. So it has kinetic energy in the motion of the spring, and then it also has potential energy, which is stored in the spring itself. And so it will turn out that at the turning points, right, the potential energy is a maximum, and the kinetic energy is zero. It actually holds still for one little brief instant in time. All the energy is located in the potential. And again, remember that the potential for a harmonic oscillator is 1/2 kx squared. When it starts to come back down and it goes through the middle of the system, the potential energy is now zero, right, and the kinetic energy is a maximum. So you can plot here energy versus time. And you get some kinetic energy function, which looks like this. You get some potential energy function, which looks like this. Imagine that that's the potential energy. And then if you add them all up, you get a constant. So that's how you might think about the energies of these systems. Now, one important consequence of this, and I'm not going to derive this result, although you can work through it on the worksheet, is the frequency at which the oscillator moves. Right? So that was omega in that previous occasion. And omega is given by this formula here. Omega is k over m to the 1/2. Right? Quick comment about units and quantities. Omega here is what we call an angular frequency. It's measured in radians per second. When you think about frequencies, what you might often think about is nu. This is often called a natural frequency. This is cycles per second. And you can relate these two simply by multiplying them by the number of radians in a circle. Right? So omega, the angular frequency, is 2 pi times nu, the natural frequency. Because the oscillator actually holds still for that one little moment in time at the turning points, and it's moving very quickly in the middle, it will turn out that the oscillator spends most of its time at the turning points. Right? That's where it hangs out most frequently. And last but not least, I mentioned that the energies of these systems were constant. They're frictionless idealized systems. But the other important point is that the energy is continuous. If I had some spring and I gave it this much energy, I could imagine giving it a little bit more by pulling it further. And if I pulled it further, I could give it a little bit more and a little bit more and a little bit more. There's nothing which is limiting the amount of energy that goes into the system. All right, those are classical harmonic oscillators. Right? I am going to next talk about the quantum harmonic oscillator, and I'll do that in the next video. See you then.